So if we continue talking about entropy and our new state function entropy, entropy, as you may recall, is a measure of the ways that energy, the number of ways that energy can be stored in a system. It's a measure of the spread of energy. That's what we kept saying before. The number of ways that energy can be stored is the spread of energy. Okay. You may remember, or you may not, seeing some of these speed distribution plots last semester when you talked about gases. Gases have a wide range of speeds. A single gas in a chamber has a wide range of speeds. This top value is called the most probable speed, but there are lots of molecules moving slower than the most probable speed, and there are lots of molecules moving faster than the most probable speed. But these two traces are for different temperature gases. The gas that has a smaller most probable speed is a cold gas, and the gas that has a higher, larger most probable speed is a hot gas. Maybe you remember that, maybe you don't, but yeah, we like to remind you of old news when we can. Today, we're going to talk about the second law of thermodynamics because it deals with entropy. The second law of thermodynamics says, for any spontaneous change, the entropy of the universe must increase. What? Yeah, for any spontaneous change, the entropy of the universe must increase. But the other day, we said sometimes entropies that, when a reaction has an entropy that decreases, that reaction could still be considered spontaneous. We talked about freezing water to make ice. That is making a more ordered thing. Ice is more ordered, has less entropy than water, but that reaction still happens spontaneously at certain temperatures. Well, the mathematical operation, the mathematical statement of the second law of thermodynamics says, for any spontaneous change, the entropy of the universe must increase. But the universe is composed of the entropy of the surroundings and the entropy of the system. All of these are change in. The entropy of the universe must increase. This value must be a positive value in order for this reaction to happen. But the surroundings could be a negative value. The change in entropy of the surroundings could be a negative value, but that means the change in entropy of the system has to be a greater positive value than the surroundings is a negative value in order to make this additive property overall positive, right? Okay. Before I go on to the next thing, instead of system, we're going to call it reaction more often because we talk about reactions in here, but the second law does talk about system entropy and surrounding entropy, but we're going to call it delta S of the reaction and delta S of the surroundings, which is everything but the reaction. Okay. Entropy is transferred by the flow of heat. What? If I have a hot brick and a cold brick, heat energy is transferred from the hot brick to the cold brick. The cold brick absorbs heat. The hot brick loses heat, releases heat. That heat energy that's transferred, when the heat energy is transferred, so is entropy. When heat energy is transferred, so is entropy. These little Q cartoon guys are carrying entropy with them from the hot brick to the cold brick. They're creating more entropy, a higher entropy state in the cold brick than existed before. Okay, what does this mean? What does this have to do with the second law of thermodynamics? Well, the second law of thermodynamics says, for any spontaneous change, the entropy of the universe must increase. Okay, cool. What do we do with this? The entropy of the system is much easier to measure. The change in entropy of a system, of a reaction, is much easier to measure than the change in entropy of the surroundings. So let's go through a couple of transitions. How do we measure the change in entropy of the surroundings? Well, first, we measure the change in entropy of the system by measuring the heat transferred into or out of the system. So we have the heat transferred into or out of divided by temperature. That tells us the change in entropy of the system, the change in entropy of the surroundings. So heat energy is something that's easy to measure. Like with a thermometer, you can measure temperature, which tells you how much heat energy was absorbed or released. But heat is something we're kind of familiar with from last semester. And you might remember from calorimetry days, oh boy, calorimetry days. You might remember from calorimetry days that if a system loses heat, and losing heat is a negative sign, if a system loses heat, the surroundings is going to gain that exact same amount of heat. if the surroundings loses heat, the system is going to absorb it. So it doesn't matter where you put this negative sign. What this is saying is the system and the surroundings are equal and opposite. So whatever heat enters or exits the system, the exact same amount of heat does the opposite thing, entering or exiting the surroundings. So what do I do with that? I can take my delta S system and instead plug in delta S surroundings, and instead of Q of the system being positive, I plug in a negative value here. So I can say delta S of the system, that's somewhat easy to measure, is equal to Q system over T. Okay, I'm not really going to do much with that. But delta S of the surroundings is related to negative Q of the system. What's lost by the system is gained by the surroundings and vice versa, over T. You may remember that when you talked about Q and calorimetry stuff long ago, that's related to delta H. So we're going to make one more transition here. Delta H of the system over T, negative, delta H of the system over T is equal to delta S of the surroundings. Because when heat is transferred, so is entropy. So we can relate delta H and delta S because heat energy transfers entropy. I know that's confusing. Let's keep working. All right, let's see what we can do with this. Why do exothermic reactions tend to be spontaneous? Well, let's explain. The second law of thermodynamics says, for any spontaneous change, the entropy of the universe must increase, aka delta S universe must be a positive value. So let's examine a system, a surroundings, a setup, a universe like this. If heat is leaving this system, that means this reaction is endothermic or exothermic. Heat leaving, heat exiting. It's an exothermic process. An exothermic process means delta H is positive or negative? Negative. So this is an exothermic process and delta H is negative. We just said a moment ago that delta S of the surroundings is equal to negative delta H of the reaction over T. So that means delta S of the surroundings will have a positive value because it's a double negative, and we don't like no double negatives. So negative times a negative, that becomes a positive value. Delta S surroundings is a positive value for an exothermic process, right? Delta S surroundings is greater than 0, aka it's positive. So we said down here delta S surroundings is positive. So delta S surroundings is a positive value, and the surroundings must increase by a greater number than the system decreases in order for delta S universe to be positive. Exothermic reactions are spontaneous in general. They're typically spontaneous because delta S surroundings is increasing by more than delta S system is decreasing. This is confusing. It's hard to get all that I want to say out, and certainly not coming out clearly, but we're going to try again. This one is an endothermic reaction. Heat is going into my system in this endothermic reaction. So if we go through the same setup over here, delta S surroundings is equal to negative delta H of the reaction over T. So this is negative times a positive. It's still going to be a negative value. So delta S surroundings is a negative value. So in this case, it's going to mean that because delta S surroundings is negative, in order for an endothermic reaction to be spontaneous, the system must increase by more than the surroundings decreases to give you a positive value overall. This kind of change is much more frequently going to lead to a positive delta S universe. Exothermic reactions are much more likely to be spontaneous than endothermic reactions because the surroundings is such a large contributing factor while the system is small. Maybe we understand that, maybe we don't. Let's see if we can write a couple more things about the second law of thermodynamics. Delta S universe equals delta S reaction instead of system. I'm going to say reaction. Delta S surroundings. If we take this second law and translate it into delta S surroundings is negative delta H of the reaction over T, we get a delta S universe equal to, I can't write and talk at the same time. Delta S universe is equal to delta S of the reaction minus delta H of the reaction over T. The cool news about this formula is that our two variables over here are both related to the reaction now, and it is much easier to measure variables related to reaction than it is to measure directly a universe variable or even a surroundings variable, because there's so much that can be lost and gained by the surroundings. So this is a fantastic formula that puts our reaction as our variable in both terms. Okay, where are we going from here? We've said, in general, exothermic reactions tend to be spontaneous. So I'm going to put a negative sign for delta H, a negative sign for delta H, and I'm going to put that in green because, in general, those tend to be spontaneous. Hold on. I'm going to put a positive sign in red and a positive sign in red because, in general, endothermic reactions tend to not be spontaneous. What the heck are you doing? Yeah, hold on. I'm going to be dividing by a Kelvin value, and we're never going to have any negative Kelvin values. It's not a thing. So I'm just going to say this whole term right here has these signs. Okay. Bear with me. Hold on. In general, delta S reactions that are positive tend to be spontaneous. Nope. I've got to make sure that my signs align to give me all combinations. Sorry. This one does not belong. In general, positive delta S system, delta S reaction is spontaneous. And negative delta S system, delta S reaction is not spontaneous. All I've done is positive, negative, 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 positive, positive, negative, positive. I've given you the 4 combinations of signs that are possible, but I color-coded them just to say this one typically happens, this one typically doesn't, this one typically doesn't, etc., etc. If I have a positive value, if I look at my top one, positive value minus a negative value, positive minus a negative is always and forever a positive value, right? Positive minus a negative, always and forever a positive value. This is an exothermic reaction that creates a more disordered system, more disordered products. Delta S of our reaction is going to be positive. The cool thing about color coding is this was green, both said go. We would call this an enthalpy and entropy driven reaction. Yeah. This one says no, and this one also says no. A negative minus a positive is going to always and forever be a negative value. So this is never spontaneous. At no temperature, never ever, you could not get a reaction like that to work. I should have said up here, this one is always spontaneous. At all temperatures, that top reaction is spontaneous. At no temperatures is that bottom reaction spontaneous. When you do a negative, I'm looking at the second one now, the negative minus another negative, we don't know if that's spontaneous or not. It depends on the size. If this term is larger than that term, it will be spontaneous. But who knows? In the third one, who knows if it's spontaneous or not? If this term is larger than that term, it will be spontaneous. But we don't know. So the thing that I summarized over here and left out was the temperature. The temperature is going to determine the magnitude of these terms. So these two middle equations are known as temperature dependent. I know all of this stuff is confusing. Bear with me. It's going to get better. It's going to get clearer. It's going to get easier. Bear with me. Let's move on. Okay, reaction conditions that favor spontaneity. We said, in general, a positive delta S favors spontaneity. A negative delta H favors spontaneity. Let's look at this reaction. I'm going from 4 molecules in my reactant beaker to more than 4 molecules in my product beaker. Delta S reaction is a positive number. If I tell you that heat is leaving, heat energy is leaving, enthalpy is leaving, that's a sign of negative for delta H, which relates to delta S surroundings. That makes delta S surroundings positive. So when surroundings is positive and reaction is positive, delta S universe is always and forever positive. Okay? That's an always. If I'm taking a lot of moles and condensing it to not many moles, delta S reaction is negative. If I'm telling you that I'm putting enthalpy in, delta H reaction is positive, meaning delta S surroundings is negative. When surroundings is negative and reaction is negative, delta S universe can never, ever, ever be positive. This is always, this is never. It's too many clicks backwards, but that's my green top row condition versus my bottom red row condition. Always and never. There are some conditions that are temperature dependent. We're calling them interesting according to my slide. If I'm taking a lot of moles and making them more ordered to fewer moles, delta S reaction is negative. But if I know that enthalpy is leaving, delta H reaction is negative, which means delta S surroundings is positive. So delta S reaction is negative. So this is a negative. This is a positive. Delta S universe is positive sometimes when the surroundings is larger than the reaction. Delta S universe is positive. Because the surroundings term is related to delta H, we say delta H drives this reaction forward. If you look back at my color coding, the delta H was green when it's negative. The delta S reaction is red when it's negative. The green one is the driver. We'll say it some more. Don't lose me just yet. Okay. One more condition. I'm taking a very ordered system because there's only 4 molecules, and I'm splitting it into more molecules, so delta S reaction is positive. If it's endothermic, enthalpy is going in, delta H is positive of the reaction, so delta S of the surroundings is negative. If delta S reaction is positive, delta S surroundings is negative. How do you know the sign of delta S universe? It's temperature dependent. But this term must be larger than that term. The reaction must be larger than the surroundings in order to get this reaction to happen. We say entropy is what's driving this reaction forward. We did all of this talk, and we didn't really even put any numbers in here, but the chem activity that you're doing with this guy does have numbers in it. And we're going to take our delta H of our reaction and convert that to a delta S of the surroundings. We're going to take our delta S of the reaction and add our surroundings and reaction together to get delta S universe. If delta S universe is positive, that reaction is spontaneous. If delta S universe is negative, that reaction is non-spontaneous. I don't like how this video has come together, but I don't have time to re-record it. I don't know what I would say differently if I had a chance to, so I'm sorry, but you get what you get sometimes. Goodbye.